Just beyond the edge of my city, you can find the Great Salt Lake, one of the largest hypersaline water bodies on Earth. Since 1959, the lake has been divided in two by a railroad causeway, which separates the rose-pink waters of the north arm from the blue waters of the south arm of the lake. Since construction of the causeway, the waters of the north arm of the lake have been nearly saturated with salt. With the exception of a brief period in the late 1980s and early 1990s, the salinity has remained near 27%, almost 8 times as salty as the ocean, making the waters essentially uninhabitable. Because several rivers discharge fresh water into the south arm, however, its salinity is lower, only about 9%. And it supports a huge population of salt-tolerant brine shrimp and brine flies. The salinity of these waters is of great importance to the ecosystems that they support, and it varies over time as the mixture of salt-saturated lake water and fresh river water varies. The mathematical description of this relationship is a simple but widely useful set of equations called a mixing model. The mixing model starts with the recognition that in a two-component mixture, the total amount of material, for example, water in a sample from the Great Salt Lake, is the sum of the component parts, in this case, lake water and river water. If we have measurements of the two of these terms, we can solve for the third. But what if we don't have the necessary measurements? For example, if we want to know the lake water-river water mixture at a given point in the Great Salt Lake, how could we make such a measurement? One solution is to use tracer concentrations. If our two sources have different concentrations of a conservative tracer, say salinity, we can write a second mass balance equation that describes the amount of tracer in the mixture as a function of the tracer concentrations and amounts of the two sources. Rearranging this equation shows that it represents the tracer concentration in the mixture as an average of the concentrations in the components weighted by the fractional contribution of each component to the mixture. The weighted mixing equation can then be rearranged to derive an unmixing equation, which gives the relative contribution of the two sources as a function of only their tracer concentrations. This is great. We now have a way to quantify our mixture using something that we can measure, the tracer concentrations in the two components of the mixture. Let's apply it to our Great Salt Lake salinity example. Taking data for the Southern Lake in 1974, we estimate that the salt-saturated lake water has been diluted with about a 56% contribution of fresh river water. The same approach can be applied using stable isotopes as a tracer. The commonly used mixing equation looks very similar to the one that we just used with salinity. Let's apply the isotope tracers to the Great Salt Lake mixing. Here we see the spatially distributed impact of freshwater inflow on spring season hydrogen isotope ratios across the South Bay. We'll take the highest, most evaporated values to represent the lake water component and use independent data to specify the isotope ratios of the river water. From this, we can estimate that a local dilution of the South Bay lake water by as much as 51% river water in parts of the sampled areas. In applying isotope ratios in mixing calculations, it's important to recognize that the mixing equation shown before is an approximation. We can see that by re-deriving the isotope tracer mixing equation, starting with the definition of an isotope ratio as the ratio of heavy to light isotope concentrations. To calculate the total amount of tracer in any of the mixing equation terms, we must multiply the ratio by the concentration of the common lighter isotope. In practice, the concentration of the common isotope is always close to 1, and if we drop this term, the resulting mixing equation is equivalent to the delta approximation shown earlier. In many mixing problems, we want to consider contributions from more than 2 potential sources. One solution is to take advantage of multiple tracers, which may allow separation of contributions from 3 or more sources. Bayesian statistical analysis can also be used to constrain the most likely mixing solutions in situations with a limited number of tracers or many possible sources. Lastly, a good mixing model application should include some assessment of uncertainty. There are several approaches to select from. However, if we consider the unmixing equation as the ratio of 2 tracer concentration differences, we can see that the sensitivity of our estimated mixing ratio to one common source of error, uncertainty in the measured isotope ratio of the mixture, is inversely proportional to the isotopic difference between the 2 sources. This highlights a universal rule for mixing models They are most useful where the components to be unmixed differ dramatically in their tracer concentrations. Thank you for listening, and please be sure to check out some of our other videos which provide background and context that may be useful in reviewing this one.